Hello and welcome to NLP Models for Climate Policy Analysis Part 1, the tutorial of Climate Change AI. My name is Tobias Szymanski. I'm a PhD student at the University of Zurich, and I'm going to guide you through this tutorial. It's going to be a high-level guidance, so I'm not going to talk about the code in details. The code is pretty self-contained, and a lot of descriptions are in the code. But I will guide you through why we do this, and what are the methods and how we apply them on a general basis. So let's get right into it and talk about the table of contents. I will introduce you to who I think is the target audience for this tutorial. We'll give an overview and a motivation. We'll also talk about the data and the model pipeline we're using, and finally about model evaluation. So who are we targeting with this tutorial? First of all, we're targeting climate scientists that seek to explore NLP technologies to analyze academic papers or generally company disclosures. We also search for data scientists with a minimal background in machine learning. So I'm assuming that you've heard the basic terms and the basic terms and methodologies already. But I'll try to explain it anyhow. But these are the two requirements I would have for this tutorial. And yeah, let's get right into it. Why do we do this? In general, you see or you might have encountered that lawmakers, regulators, but also politicians write a lot of climate-related text these days, climate-related scientific reports, and there's a lot of climate talk from companies as well. So in its essence, climate change has become or climate science has become a data problem, and data problems are usually well addressed with, or the big data problems are usually well addressed with machine learning methods, and so is natural language processing one of the sub-regions of machine learning that can help to actually assess climate-related relevant texts. So what we're going to talk about is how to, we will explore the data set, and we will build a pipeline for a simple machine learning model. Then I'll demonstrate how to use a support vector machine classifier with to perform a classification task. And finally, we will train and evaluate also transformer models. So the most modern architecture, also well known because of ChatGPT, where T stands for transformers. So why do we do it? I already said that, there's a lot of data out there, but let's make it very concrete. Let's make it one use case, which we probably know as climate scientists, or at least people that are interested in climate change, that are the IPCC reports. And the IPCC reports are a synthesis of all the scientific literature on climate change that is out there. So the reports are published every 6 to 7 years, and for each report, the IPCC authors try to actually combine the climate knowledge that is out there in the field. So now, what problem do you encounter if you do so? You see here that while the first iteration of the IPCC reports actually had something like 1,000 publications included, the last cycle actually had to consider something like 375,000 publications. And how do you deal with this large amount of data? How do you actually classify? How do you cluster? How do you structure that? And we're going to talk about two methods that we actually want to use today for evidence-based, for machine learning assisted evidence synthesis, which basically is how can we come up with results out of a large amount of data? How can we synthesize, and how can we ease the work for a human that needs to assess and needs to write these reports? We're going to do two things. We first of all identify relevant studies. So we use a binary classifier that can be trained with human screen data. And we also want to classify these relevant studies into different regions. So for example, you could be an expert on forestry, you could be an expert on water-related issues. And you really want to assign these really relevant reports to the expert that has the relevant knowledge. So it's only water-related reports to the water expert, and so on. We are going to rely on supervised methods. So as a short reminder of that, supervised methods are those where a human have assigned a label, and the machine learns basically the correlations through the training data, and then tries to predict unseen data. As I said, I quite have assumed that you already have some limited knowledge to that. You can follow this tutorial very well irrespective of that, but these are the terms that I would assume that you've already heard to some extent. So what do we use? We use 3 libraries here. We install the datasets library, the transformers library, and the accelerate library. In its essence, it's just packages that we will use to run our models. And you should probably be familiar with the transformers one that's from Hugging Face, where we can load a large amount of models. Okay, let's get right into our data source. There is a large amount of data sources that actually have bibliographies or bibliographic databases that have a lot of sources included. We are going to use OpenAlex that tries to be extremely comprehensive. For use cases, it's extremely important, obviously, to be comprehensive, but for our case, it's just important to have a data set with which we can train and classify. Let's get right into this data set. We'll have a labeled data set and an unlabeled data set. The labeled data will have a column that is called include, so whether a report was actually used for IPCC or for the IPCC reports, or whether it was not used. And then we have an unlabeled data set, which comes from the OpenAlex database. And then we have in this data set one column that is called seen, so whether a human has actually screened it. So we know whether a human has screened it, and then we also know whether it was included into the final IPCC report or not. And these are basically the dimensions along which we will have our first classification tasks. So let's load and have a look at the data. As I said, I will not go through every line of code, but we look at the data set briefly, and we'll see that we have around 25,000 rows, and these rows look as follows. We have an ID, a URL, a title, publication year, and an abstract, and of course an author. So we have some kind of metadata to work with. In its essence, we want to look at the dataset really briefly, how it might be structured, and we see, okay, we have a lot of publications, or we start from 1990, and we have a lot of publications from 2010 on. As I said, it's probably 1,200 publications per year. It's probably not all the publications we have on the issue, but it's really important to just have this data set to learn how we can develop these methods. And then further down the line, if you use it yourself, you can obviously use it on large amounts of data on your own. So let's get right into the model pipeline. For the model pipeline, as I said, we will do a supervised learning task. So we need some data for support vector machines, so for our SVMs. And we'll use labeled data that we have prepared for this tutorial. And we'll have a look at the labeled data. And we'll see something reoccurs, something we've seen before. We have the title and the abstract, so we know these ones. And then we have this seen column. So the seen column means, as a repetition, that the human has had a look at the source, and then the include column means that the report was actually included into the IPCC synthesis. So we see also 5 more categories here, which will come to play later. Just as a preview on that, we'll see that these sources are also classified by 5 different categories. So it could be terrestrial, it could be, for example, mountains and snow, it could be rivers and lakes. So depending on where the what the source is talking about, we also have these 5 categories. But for now, we'll concentrate on the seen and include. So we'll create a data set that includes the unlabeled and the labeled data set. So we basically create a synthesis of the two and drop all the data sets that don't have an abstract. Because further down the line, we will use the abstract, which is basically the textual source, to classify our text. So we combine this, we still see seen, include, and all the other categories. So now having a large data set. Let's have a look at how the labels are distributed then. And we can see that, we have 2,500 data points that are seen, that are screened by the human, and we have 18,262 that are not screened. And within these 2,500, we have around 1,300 that are included, and equally much, around 1,200 that are not included into the final report. And we also see that we quite fairly have a distribution of a fair distribution, a fairly equal distribution of all the subtopics. Well, mountain, snow, and ice is obviously the least, and the most is obviously terrestrial. But yeah, every class has around 180 data points. That's important later on when we train the classifier for this task. But let's go step by step. The first step we're gonna do anyhow for all these tasks is to create a train test split. If you still recall about like the supervised methods that you know in machine learning, then you need a train set to train the method and a test set that the method has not seen to kind of verify how good the performance is. So this method in essence just splits up any data frame. For us, it will be the data frame we just looked at, and creates a train and test split. Okay, that looks good. So now, if you're familiar with machine learning, you probably know that in machine learning, basically a method always learns of so-called features. For a normal machine learning method, let's call a regression and machine learning method, it's like very simple because you have, for example, a house price is predicted by the number of square meters of a house. But for text, it is not as straightforward. For text, you have these words, and these words have to be translated to numbers for the machine, right? Because the machine will work with numbers. So we will have two tasks to solve in the end. But first of all, we want to have features out of these texts. And for that, we use two methods. The first one is a very simple one, the count vectorizer, and the second one is the TF-IDF vectorizer. I'll explain in a second. First, we look at the count vectorizer. The count vectorizer is a very simple idea. If you have these texts, for example, climate change is impacting human systems. Climate change is caused by fossil fuels, and system change, not climate change. And the idea is very straightforward. You just count the occurrence of the words. So in this sentence, climate appears one time. This sentence, climate appears one time. This sentence, one time. Change in turn appears one time, and two times. And by just counting the occurrence, you basically transform the sentence into a vector. And how that would look like in a technical representation, we can have a look here. So now we basically transformed this first sentence, climate change is impacting human systems. So we see climate change is impacting human and systems appears all one time. Now, this is a very naive method, and this explains the general idea, but as we all know, a word like is should probably not have as much of an impact as, for example, climate and change, because climate and change are indicators that at least this sentence belongs to the climate change class, while is generally not a good indicator. So what people have thought about is this method called term frequency inverse document frequency, which in a nutshell is just the rarer the word is, the more weight it will get. Because the intuition is that words like is, words like you, are, and will have a occurrence that is much higher than words like climate or change. And therefore, climate and change are more useful indicators than the normal is and by and whatever. So when we visualize the same sentences with the TF-IDF, we will see that the words, for example, change get more weight, climate gets a tendency of more words, human get more, and impacting gets more. However, this method is not yet really sophisticated, of course, because we only have 3 sentences in our training database. So having much more sentences in the TF-IDF vectorizer, so much more when you actually create these vectors, will help a lot, because then obviously these very common words will appear more often. But yeah, let's move on with this. notion, because it's just like an example, and try to identify how we can actually learn from these features. Learning from these features, again, is just a machine learning problem, right? We have now a numerical vector, and this numerical vector is basically indicating, well, how often do these numbers appear, or how these words appear, and basically with this TF-IDF, we have a bit of more of a nuance in it. So what we can do is actually, similar to all the others machine learning problems, we can build a decision boundary between these two or between differently labeled sentences. So what we do is we load the support vector machine here, and we also load some text. And now importantly, of course, we need labels. So what we do here is we have a task where we have climate change is impacting human systems. This is actually also the labeling target. So every time climate change has an impact, we label it as 1, while climate change is caused by fossil fuels, so caused by, has a label of 0. So we basically want to learn the machine to distinguish between these two things. And we built this classifier, very straightforward. You can have a look at the details of the code later on. But importantly, we want to classify these sentences now, and we see that the sentence climate change is impacting terrestrial systems is actually predicted with the label of 1, while machine learning will solve climate change is predicted by a label of 0. However, obviously, we only had 10 examples to learn this machine. There's always biases in it, right? We have this Coca-Cola as a company that produces sugar drinks. So could be that the word company or the word produces or sugary drinks or something like that is actually an indicator for the 1 label, so the impact label, which is obviously a fault, but due to the limited training data, we get a prediction of 1 here as well. So already shown some potentials, but also some limitations with these support vector machines. Yeah, what we can do as well is we can apply this support vector machine to our whole 2,500 data points of include or not include. And now we will quickly train this machine and also already see kind of the results of how good we are. Yeah, to recap, to use this time, this 20 seconds that it takes to run, to recap on what we've learned. Now we basically have learned that we can extract features, numerical vectors, from text through count vectorizer or a TF-IDF vectorizer. For these methods, we take all the training sentences, build a large scale of vocabulary, and then basically take each of the individual sentences and basically count, or with TF-IDF, we have a bit of a more nuanced of counting mechanism. And then once we have counted them, we build basically a decision boundary with the support vector machine. And then we can classify our 500 test sets. And we now can see that we actually classify 83% of our test set right. So we already can see, okay, for this include, non-include task, we actually are quite fine in the classification. About the other metrics, we'll talk later on, but for now, I think this accuracy serves us as an indicator. Now, let's move on to the next task. The next task is multi-label problems. And to not be confused with multi-class problems, multi-label problems mean that the sentences or the objects to classify can belong to multiple classes, while for multi-class problems, it would be exactly 1 class. But let's have a look at how this could look like for our problem. We again turn to our data set of these 2,500 labeled data points, and we see here these 5 classes. As you can see here, this is only terrestrial. Next one is again terrestrial, and the next one is again human and managed, and so on. So majority of the time, it's actually only 1 class, but we'll have a look at how this looks on a scale. So we'll see for the majority of the time, there's actually only 1 class. Sometimes there's also 2 classes, and very rarely there's also 3 classes active for a sample. So it is a multi-label problem, but obviously not as severe. Yeah, we can do the same actually as we've done before. This time we want to sample 200 samples because it takes quite a long time to train this multi-label classifier otherwise. And we again use the abstract as the vector to predict. And we will again use TF-IDF vectorizer to form these features. And yeah, we train this classifier real quick and then also try to predict some limited samples. Again, this is something that is up for you to discover how to play around with these things. But for now, we classify these two texts. So climate change has affected butterfly phenology. I don't know if I pronounced that right, but yeah, in North America and so on and so on. So it talks about some, I would say, some geographies. And then here we have rising temperatures have contributed to increasing heat related to mortality in cities across Europe. Let's see. Okay, the first sentence, terrestrial, that makes sense. There's North America. We have these butterfly national parks, so we have these terrestrial impacts. While the second sentence does not belong to any of the categories. Not coastal, not human and managed, not mountains and snow, not rivers, and not terrestrial. So this seems okay. And it's kind of a demonstration of how we can address this multi-label problem. Okay, so far so good. I hope you could follow this high-level overview until now. Now we're gonna go to what's transformers. And maybe the major differentiation between that is that transformers are already pre-trained models. So transformers already have a language understanding. If you want to translate it to discount vectorizer logic, then they already have seen a large amount of vocabulary and they have seen this large amount of text. So we don't have to train from scratch, but only in this, for these transformers, we only fine-tune them. And specifically, we fine-tune a model created by my group that is called ClimateBird. And ClimateBird is basically a model that was specifically pre-trained to understand climate texts. And that's something really powerful, because climate texts have their own nuances. Think about how, for example, water, or how, for example, forest, or the word climate itself could mean different things in different contexts. So for example, if we have a good climate in our work, and that's something different if you have a good climate in our earth, right? So you have to really understand these nuances, and ClimateBird is specifically trained to understand these nuances. And what we can do, because it already is pre-trained, we only do fine-tuning on this model. So we only adjust the last bits of the classification rather than the language understanding itself. Again, we define a set of texts that are the same texts that we've seen before. Climate change is impacting human systems. Climate change is caused by fossil fuels, and so on. So what we do now is actually we use, since we already have this predefined vocabulary and this predefined model, we use both the model and the vocabulary translator, which is called tokenizer, for applying this model. So the tokenizer, again, we'll see an example in a second, will transform the text to a vector. And how this vector will look like, we'll have a second here. So now we see this text is called climate change is impacting human systems. And we now have the input ideas, so basically the translation of each word or each token, which translates more or less to a word. But for now, we can basically see that it starts with 0, then it goes to this number 40,466. So you can see, maybe translating one by one, which is not 100% accurate, that climate would be 1, then change would be this 40,466, and so on. Then you would basically have a numeric representation. Tokenizers function a bit more complex. That's why you have additional numbers here and a 0 in the beginning, but the idea stays pretty much the same between the count vectorizer and then the tokenizer to kind of get this numerical value. However, these transformers have certain weights assigned to all these numerical values, so it's only basically a means to understand the text. Yeah, what we can do now is to actually create a data set again, a train and a test data set, tokenize this whole data set. And very briefly, we can actually train now or fine-tune now this model. Well, you don't need to understand every bit of the code. It's probably good to see that here we load a model, and then we create a trainer object which loads the model and the data set. So as you can see, this is much more high level because these transformers are basically bundled in these packages, which makes it very handy. We see we trained over 3 epochs, and now we have new text which we can predict. Yeah, as we can see, these predictions are not really informative because now we don't get probabilities, but we get so-called logits out of that. But it's very straightforward to transform these logits to probabilities. As we can see here, now we have probabilities and probabilities for both labels. So we can have this one label and the other one, and the higher probability is kind of the probability that basically the label will be assigned to. Yeah, this is basically the way transformers will work. We now want to actually train a bit of a transformer that includes all these steps. So we train, predict the probability, and we see this is the same. This is this outcome. So basically a label of 1, a label of 0, and a label of 0. If we go back to the texts, then we see this is actually accurate. The first one is a label of 1. Again, this impact on terrestrial systems. Machine learning will solve climate change. There's no impact of climate change. And then the Supreme Court made a series of decisions on personal freedom. Again, this different or the 0 label, if we look back at these probabilities, 0, 0, and the first one was 1. Okay. Now we turn our attention again to multi-label problems. This again, I will just run this code. This again is just the way how to implement this problem. And if we run this successfully, then we will also see that we now have can train this model and get predictions that are for not only 1 but for 5 categories. And yeah, while I see that these details will probably take some time, I would just like you to take the time and get familiar with the functions and get familiar with the models to understand this in detail. We'll wait a minute to actually get these results done, and then we'll have a look at how these multi-level classifications will look like. But in essence, we will just see a similar vector that has 5 entries, and then for every entry we'll have a probability, and these probabilities will signal how much, how probable it is that this one sentence belongs to this class. Okay, now we have it. We see that these probabilities are basically a series of probabilities. I will not go into the details now. I will just say, okay, we see these probabilities are here for these is above 50. This is the highest probability. You can have a look at the samples, but please be aware that we only trained on a very limited amount of data. So these are basically this is basically only code that shows you how it can be done, rather than actually take these classifiers for granted. Okay. Much more important is actually a step that we already kind of addressed, and that is model evaluation. And the question obviously arises on how do we evaluate our models once we have trained these classifiers. And yeah, we will go through the metrics real quick on which metrics you can use or which metrics you probably should use. The first metric is actually the accuracy. That's something that is very straightforward. So we have created these 2 vectors here, and these are the predictions. And then we predict how much do we actually predict the same way this ypred. How much is this coherent with the y true? And we can see, as already has been shown, that we get 8 of the 10 predictions right. So we can see here, this one we got wrong, and this one we got wrong. However, very importantly, we see that the y true majorly has zeros. So if I would predict every single of them as 0, then I would also arrive with 80%. So there must be some more nuance we want to put to this, and more nuance can be created with two metrics called precision and recall. And for this precision and recall, we need two concepts. The first one is false positives. So where a sample is negative and is predicted to be positive, and false negatives, where a sample is positive and is predicted to be negative. Maybe you're already familiar with these. So precision is basically a classifier identifies 100 as true, and precision would tell you how many of those samples are actually true. So within the true ones, how many are actually true, while the recall tells you if you have 100 of true samples, how many of those samples your classifier will identify. So how good are you in actually identifying the true ones versus how good are you actually in, or how bad are you actually in exaggerating the true ones? So two nuances. And then the F1 score will be the weighted average between the precision and the recall. Let's have a look at our predictions. We've seen above here that we had this 1 out of 2 predicted positives are actually positive. If you look at the example above here, then we have predicted 2, and only 1 out of these 2 is actually predicted right. While on the other hand, we have two true positives, and we only identify 1. So the recall will also be 50%, and if we go down here, then we also will see that the recall is also 50%. Okay. Well, thank you very much for listening to that. I think it was a sprint. We can also see that the accuracy, precision, recall, and the F1 score are also ready-made metrics already. So we can see this here. Yeah, now that we finished this, we go to the exercise. I'll just introduce the exercise real quick. It was definitely kind of a sprint of how we got here because of the limited time, but I think it is worthwhile to have a look on your own through data and code and try to understand these details and the nuances on your own, and then advance towards an exercise where we actually use a ready-made classifier called Climate BirdNet 0, and we want to see how well this functions. So what we will do here is we have a sample of 20 texts, and we will classify these 20 texts with Climate BirdNet 0. Then we will have a look at the output, and importantly, you will do the classifications, you will do the predictions, and transfer these predictions into numerical values, and then you will also create these metrics. And finally, you will also try to look at the mismatch samples of what was going on there. If you don't succeed, you will also have a solution, which I would suggest you only open up once you've understood everything. But yeah, for now, I think I'll leave you with that. Thank you very much for your attention, and I hope I see you in the next tutorial.